Okay, so you've seen that the following is an equivalence relation, right? This property that A and B are related if and only if n divides their difference, A minus B. And it turns out that there's a special name for this equivalence relation called congruence, or congruence modulo n, if you want to emphasize what the number n is that we're using. And again, just to give an example here, we can talk about, say, the equivalence relation congruence modulo 7, where under this relation, the numbers 12 and 19 would be equivalent. And we would write that as follows. 12 is congruent to 19 mod 7. Again, just to emphasize that it's 7 is the modulus that we're using. Right? And it's easy to check. Does 7 divide their difference? In this case, yes. 12 minus 19 is negative 7. Right? And you can write negative 7 as negative 1 times 7. Now, what's important here is that this congruence relation actually tells us something about the remainders of these two numbers, A and B. Right? So if we know that n divides their difference, what that actually tells me is A and B have the same remainder when you divide by n. Okay, so why is that true? Again, let's look at our example here above, 12 and 19. So 12 is equal to 1 copy of 7 plus a remainder of 5, whereas 19, well, there are two 7s in 19, right? Because when you divide when you divide 19 by 7, I'm going to get 2 remainder 5. Right? And so if we know that 7 divides the difference of two numbers, that should mean that this leftover stuff, after we've separated all the blocks in groups of 7, these have to cancel out exactly with each other. Right? Just so, again, we'll be left with something exactly divisible by 7. And so this is why this result is true. In fact, this is an if and only if statement. So let me write that down properly here. If and only if A and B have the same remainder when dividing by 7. And the big idea here behind congruence is that there are applications where really we only care about the remainder of certain numbers when you're dividing by n. And I'll give you an example here. Okay, for instance, if today's Thursday, what day is it exactly 500 days from today? Okay, so we're counting days of the week, right? So Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, Sunday. And what you note about this is that every time you add 7 to this number, you're ending up with the same day. Because it's just the same 7 days over and over again. Right? So when you start at Thursday, for instance, 7 days from Thursday is again Thursday. 7 days from that Thursday is another Thursday. And so on and so forth. Which means we don't really need to count 500 days from Thursday manually, like one by one, right? We just really need to find what is the remainder, when we divide 500 by 7. Right, and so let's do the division. The remainder is 3. Which means after I've done 71 complete cycles through the whole week, putting me back at Thursday each time, I need to do 3 more days forward. So that's Friday, Saturday, and Sunday. So exactly 500 days from Thursday is always going to be a Sunday. Right? So that's one application where, we really just cared about the remainder here and not the whole 500 days. And so the congruence classes, right, or the equivalence classes, of this relation are called congruence classes or remainder classes. Right? In the sense that when you're considering the relation modulo 7, your congruence modulo 7, where we say that two numbers are equivalent if they have the same remainder modulo 7, that means, well, how many possible remainders are there? By the division algorithm, there are 7 possible remainders. A number could have remainder 0, remainder 1, remainder 2, 3, 4, 5, or 6. And so every integer can be classified into exactly one of these sets. Right? So we saw 12 was here, as well as 19. The number 9 is here, for instance, as well as the number -5, right? Because -5 has a remainder of 2 when you're dividing by 7. Right? And so on. So these sets form a partition, right, of all the integers into these remainder classes. And remember, what's nice about this is, in this particular relation, when we only care about the remainder of numbers, well, it turns out that when we're doing arithmetic with these numbers, we're actually allowed to replace any number within some congruence class with any other number in the same congruence class. So for instance, if I see 12, I can just replace it with 5 when I'm doing arithmetic under modulo 7. And I'll give an example here. What is the remainder when this product is divided by 7? 351 times 139. So one thing you could do really is to just multiply them out and then divide by 7. Right? So you're going to get something here, and then whatever this is, you're dividing by 7 to get the remainder. Okay, but since we really only care about the remainder, what I'm going to do instead is I'm going to say 351. What's the remainder when 351 is divided by 7? Well, 35 is divisible by 7, so this is actually 50, remainder 1, right? Or let's write that down properly here. 351 is equal to 50 times 7 plus 1, right? So that's the remainder. Also, 139 is 1 less than 140. Right, so this is actually 133 is divisible by 7, so it's 19 times 7 plus 6. And these are their remainders. And what this tells me is that 351 is in the congruence class of 1, and 139 is in the congruence class of 6. Which means, since we're just looking for the remainder, 351 times 139 will have the same remainder when you divide by 7 as just the product 1 times 6. Or simply that it has remainder 6. Right? And we were able to get that without having to do this multiplication on the upper left.